Alright, what is up everybody? We are in our last section for Unit 10 before our test, which is area of similar figures. So the reason why this is thrown in here is because since we're on two-dimensional area, it's kind of thrown in at the end. We dealt with similar figures when we were doing ratios and proportions a while ago, but that's okay. I'm going to quickly review all that stuff before we get into the new stuff. So remember, similar figures are shapes or figures that are the same shape but a different size, right? And so if I have triangle ABC and triangle XYZ, and I say that triangle ABC is similar to XYZ, then we can make those corresponding ratios, right? Because the similar figures are proportional. So corresponding ratios are equal, meaning sides that are in the same relative position when made a fraction or a ratio with another side that's in the same relative position. We can make three of those because there's three different sides for each one, right? Then those ratios are equal, which make them proportional. So if I were to do side AB over side XY, so notice that AB is in the same relative position as XY, and then AC is in the same relative position as XZ. Those are two corresponding ratios. And because these figures are similar, that makes them equal, right? Because they're proportional. So then if we were to put this as a fraction, right, it becomes 2 over 4 equals 3 over 6. They both reduce to 1/2. And that 1/2, we call that the scale factor, the reduced ratio. And what that means is the figure on the left is half the size of the figure on the right, or the figure on the right is double the size of the figure on the left. Okay, so how does this work for area of similar figures? Now we're still going to be using a ratio, but we have to adjust it. So let's look at those dimensions of those two triangles that I have, right? If we think about the area of each of those triangles, so for that first one, it would be 1/2 2 times 3, 1/2 base times height. For the second one, it would be 1/2 4 times 6, again, 1/2 base times height. So for the one on the left, that becomes 2 times 3 is 6. 6 divided by 2 is 3 units squared. The one on the right, 4 times 6 is 24. 24 divided by 2 is 12. So the ratio of the areas is 3 over 12. Okay, so if I were to put them and compare them into a ratio, remember a ratio is just a fraction, that becomes 3 over 12. And the reason why I'm putting the 3 over the 12 is because I'm always doing a left over right. So notice, right, like I always did left over right, left over right, left over right. I just stuck with that pattern. And you can do it however you want as long as you're staying consistent. So now if I were to compare the ratio of 3 over 12, which reduced is 1/4, to the scale factor ratio that we found in the very beginning, which was 1/2, how could I make those equal, right? So what would you do to 1/2 to get 1/4? Well, in this case, right, we have to, it wouldn't be 1/2 plus 1/2 because 1/2 plus 1/2 is 2 over 2, which equals 1. So again, how do I get this ratio to equal this ratio? And the answer is we square it, right? Because 1/2 squared is 1/2 times 1/2. That becomes 1/4. And so that is the new information today. How do we make a scale factor ratio equal to the area ratio of the same figures? And the answer to that is we need to square our scale factor ratio. So the scale factor ratio squared equals the area ratio. And that is the only new topic for today. Okay, so the way that this works is you're going to be given two similar figures. You might be given two side lengths that are corresponding for each and the area of one of those. You're trying to find the area of the other figure. Or you're given two similar figures. You're given the area for both. You're given one side length. And you're trying to find another side length of another triangle. Okay, so we're going to do two examples of each scenario, and then we'll be done for the day. So these two figures are similar. So I'm telling you that they are similar, which makes them proportional, and also the orientation of both of them is still exactly the same. Okay, so first things first, we would then make a ratio of the corresponding sides. So left over right, 10 over 18. And I would recommend reducing this. Even though we're going to use a calculator, it's going to make your numbers a lot smaller. So I'm going to reduce that to 5 over 9. So that means, 5 over 9. So that means my scale factor is 5 over 9. And again, I'm doing a left over right ratio. My area ratio is 25 over unknown. So we'll just call that x. So that's what we're trying to find. We're trying to find the area of the larger triangle without having to worry about height and base or anything like that. And because we know corresponding lengths of each triangle and we know the area of the first triangle, we can find the area of the second triangle. So remember, our formula is scale factor ratio squared equals our area ratio. Okay? So our scale factor ratio squared equals our area ratio. Now, one thing to remember when squaring a fraction, the square gets distributed to both of them. So 5 over 9 squared becomes 25 over 81. That equals 25 over x. Okay. Cross multiply, I get 25x equals 81 times 25 is 2025. Divide that by 25, and hopefully it just jumped out at us that the answer was 81 because the numerators of these are both the same. Now that's not going to happen very often, it just happened for this occasion. Okay, so then we would be done. We found that the area of our second triangle is 81 units squared, okay, using this formula right here. Let's do another one. Okay, so notice we have two parallelograms. We're given the height of each parallelogram, and we're trying to find the area of the larger one. So first things first is create your scale factor ratio. Now that's not reducible. I'd leave it as a decimal, okay? And then we're going to square it to make it equal to our area ratios. Go ahead and square that. So 7.5 squared is 56.25. 15 squared is 225 equals 60 over y. So notice, right, the numerators are not the same like our previous problem, which means we're going to have to do a little more calculation this time. Cross multiply 56.25y equals 225 times 60. That gets me 13,500. And then I'm just going to divide that amount by 56.25. That gets me 240. So the area of our second figure is 240 feet squared. So let's now switch up what we are solving for. Okay. So now I'm giving you two similar figures, but in this instance, we are going to find a missing side length. So there's a little bit more math involved with this, not too much, pretty simple. Okay, so first make your corresponding ratio sides, 12 over x. Then make your area ratio, 72 over 50. But remember, to make these equal, we have to square the side ratio, the side length ratio. Okay, so now when I do that, I distribute the square to the top and to the bottom, numerator and denominator, so I get 144 over x squared equals 72 over 50. So once we get to this point, we're just going to cross multiply these up. So I get 72x squared equals 144 times 50, which is 7,200. Divide both sides by 72. Don't mind the bell. So then I get x squared equals 100. Last step is take the square root. So x equals 10. So that missing side length for that shape was 10. Let's look at one more example, and then we'll be done for the day. So same idea. I'm given both areas, but now I need to find a missing side length of our second triangle there, right? So let's make our corresponding ratio. Let's make our area ratio, and then to make them equal, we have to square the side length ratio. So first things first, distribute our square to the numerator and denominator. So 14 squared is 196 over x squared equals 96 over 150. Cross multiply, I get 96x squared equals 196 times 150. So 196 times 150 is 29,400. Divide that amount by 96. So I get x squared equals 306.25. And then I'm just going to take the square root of that amount. So the square root of 306.25 comes out to 17.5. So our missing side length of that second triangle is 17.5. And that is it for the day. Good luck.